Welcome everyone to Catherine's thesis defense. It's my great pleasure to introduce our speaker. It's Catherine Pavlov, came from Caltech, and before she came here, she did a lot of projects at JPL for like 2 years of different projects at JPL. She also briefly worked for David here at CMU, and then really started my lab with me. So she and I started the same day, more or less, in 2016, and has been helping me get the lab out from an empty room with zero equipment and you and Joe, so 2 people to start, up to now we've had 10 grad students, 10 PhD students, and I don't know, 60 undergrads or something like. So I'm greatly appreciative of having her. For these last few years, she's been working on taking rovers and doing stupid things to them, like driving a wheel backwards or fighting against each other and trying to get the wheel stuck in the sand to sort of try and better understand how that all works. She also has done a lot with our outreach programs, helping make mini recs and mentor countless students in the lab. So I'll have a quick note that Terry, one of the committee members, is sick and won't be here, but we'll send Terry. We miss you, and we'll send you this recording. So, without any further ado, Catherine.
Thanks, Aaron. Yeah, so thanks for the great introduction, Aaron, and thanks so much, everyone, for being here, especially my committee members. Terry, we miss you and wish you were here too. But it's great to see so many friendly faces. So, without any further ado, let's get started. People who are remote, if you are encountering technical difficulties, send me a message. The format's going to be all talk for about 45 minutes, give or take. And then we'll have questions afterwards. I think we'll be starting with committee members for questions, and then it'll be open to audience members.
Yeah, I should have said, let's try and keep questions during the talk to a minimum, so quick clarifying questions. We'll have plenty of time for long questions at the end.
Yeah, I don't know if remote people can hear things going on in the room, but save your questions till the end unless they're really short ones. All right. So without any further ado, my name is Catherine, and I'm here to talk to you about off-nominal rover driving, looking specifically at terrain manipulation and degraded mobility compensation. So first off, let's talk about why we even care about rovers in the first place. Wheeled rovers are at the forefront of space exploration. You can see here on the upper left is an image of Perseverance. Perseverance is one of a couple rovers on Mars right now. And Perseverance recently collected and cached its first sample as a part of Mars sample return. So in maybe a decade, maybe a little longer, we should be getting samples of Martian soil and rocks back from Mars onto the Earth's surface, and rovers are a huge part of that equation. You can see here on the lower left is an image of Viper, the Volatiles Investigating Polar Exploration rover. This is a rover that will be launching to the lunar surface in 2024, searching for signs of water and other volatiles necessary for a sustained human presence on the moon. So upcoming mission, very cool. And if we look to the past, wheeled rovers have really driven a lot of our scientific discoveries in the solar system. This is a picture of either Spirit or Opportunity. They're identical, so I can't really tell you which one it is. And they have driven a huge amount of our knowledge about how the solar system works. One of the drawbacks to any space mission, but especially looking at rovers, is that they're very highly mass constrained. So if we can get any kind of additional functionality out of existing systems on those rovers without building new mechanisms, that's extremely useful. There's 2 key areas that we can look at here. The first is that our drive systems often have very powerful actuators used for locomotion that we can repurpose for manipulation. The second is looking at how we can get back capability when we lose some. When mobility actuators degrade, we might be able to regain some amount of functionality, because generally they'll have more capability to provide force than is explicitly needed for driving. And if we change how we're controlling things, we can get some back in the case of damage. So let's talk more about manipulation. First up, I'm talking about non-prehensile manipulation today. Non-prehensile just means non-grasping. It doesn't require a dedicated manipulator necessarily. So it can involve pushing, rolling, or any other non-force closure contact. You can see in the video here, this was taken by Dr. Jennifer King, who did some previous work using the frame of a rover to push around cardboard boxes. So she's using the rover here to do rearrangement planning, doing non-prehensile manipulation through pushing. So this is an example of what non-prehensile can look like applied to a rover. Mars rovers have also used their wheels to interact with terrain already. Both Spirit and Opportunity created small trenches or wheel scuffs in the dirt, but this was done in a largely ad hoc manner, where the rover's manipulation was sort of hand tested and pre-planned and done in a small amount, but it was sort of just, trial and error on Earth, replicate on hardware in situ. There wasn't a huge amount of planning. If we wanted to do larger scale manipulations, we need to move beyond that. So this is a pretty small wheel scuff. You can see it's less than the length of the rover body, just based on the width of the wheel. And it's good for looking at a specific sampling location. But if we wanted to sample over larger regions, it's maybe not as helpful. We'd also like to be able to predict the results of these terrain manipulations. Rather than just dragging a wheel and seeing what happens, we might want to dig to a specified depth, or at least know that we're not going to get stuck when we do this. Going back to mobility system degradation, this is a serious risk to rovers. Both Spirit and Opportunity encountered mobility loss in multiple forms. There was some amount of steering actuators getting stuck at a fixed angle, motors losing power, and even in this image on the lower right here, a rock got stuck in Spirit's wheel for a while. They were able to get this free through some careful maneuvers, but it's a very real problem that has happened. Soft soil is also a particularly large environmental hazard on both the lunar and Martian surfaces for wheeled rovers. The risk of entrapment is high when encountering soft soil, especially if you're also experiencing some amount of mobility loss. If we're looking at applying this to upcoming missions, one to look at in particular is Viper. The Viper rover has a 4-wheeled active suspension, which is potentially higher risk. Rather than a 6-wheeled passive suspension like Spirit, Opportunity, Curiosity, and Perseverance have, Viper has only 4 wheels, but each of them is able to lift up and down. So we have additional actuation there. So we've got now 12 motors, but if any one of them fails, it's potentially a higher impact because now it's impacting a quarter of our thrust-giving wheels rather than only a 1/6. We also need to consider that future rovers are going to have longer mission durations. For example, the NASA Decadal survey called for Endurance A, a mission that will have a rover traverse 1,000 kilometers on a lunar surface. For context, the longest a rover has driven is Opportunity, which went under 50 kilometers in 14 years. So going from 50 kilometers to 1,000 kilometers is going to require a paradigm shift in how we think about rover mobility. And as a part of that, we're going to need to plan for failure. We can't just say, we'll drive as far as we want, we'll design this thing to last for 90 days, and if it goes longer, great, if it dies, whatever. We really need to bake into our mission planning, what are we going to do when something breaks, because it's going to happen over a distance that long. Additionally, current rovers rely on open loop driving. Both Curiosity and Perseverance only do visual odometry about every meter to check whether they're slipping or not. So they're not doing online visual odometry, which means that you need to have good, reliable open loop driving strategies. You can't just close the loop to fix everything. Having good open loop driving strategies requires a strong knowledge of your wheel terrain interaction. So failure is a really big problem. Can we do anything about it? The good news is yes. This video here is one I took of K-Rex-2 at the NASA Ames Roverscape. Here I have fixed K-Rex's rear right wheel so that it's non-rotating, as if it had a rock jam or some other thing causing it to non-rotate. You can see on the left that without any compensation, it pretty quickly veers off the track and goes into a ditch. This is a problem. However, with hand-tuned compensation, we're able to drive relatively straight over prepared terrain. But this is hand-tuned, and it took me a couple days of hand-tuning to get this to work reliably. So that's not a great solution if we want to be driving thousands of kilometers while we're doing this and potentially encountering different types of terrain where we would have to retune every time we change our soil properties. So with all this in mind, there's a couple of questions we're going to ask. First up, how can we gain greater functionality from existing systems with minimal physical additions? And we also want to know, how can we maintain the functionality of mobility systems when they've degraded beyond their nominal state? And these two questions really lead into, how do we predict the performance of rovers operating in soft soil beyond their intended use? Whether that's because we have forced them to be beyond their intended use, or they've degraded and the environment is forcing it upon us. So here's what we're going to talk about today. First up, I'll go over non-prehensile terrain manipulation a little more, talk about what that is as a concept and why we care about it and what we're going to do with it here. Then I'll go into a model that I built that describes the soil flow around the wheel of a rover that is driving under off-nominal or nominal conditions. And then I'll talk about a Terramechanics model that I've made that's able to handle off-nominal conditions that no existing Terramechanics models could previously handle. Then I'll talk about how we put those all together and develop full rover control strategies for both open loop and closed loop control of driving during off-nominal conditions. And finally, I'll talk about what we've learned so far and what is up next for this area of research. First up, let's talk more about non-prehensile terrain manipulation. So non-prehensile terrain manipulation is any terrain-focused non-prehensile manipulation. Could be rolling snowballs like what Millie is doing here, or pushing rocks around or digging in the dirt. Rovers have a variety of uses for non-prehensile terrain manipulation. The first one, and the one I'll talk the most about today, is science, subsurface sampling. It could also use it for mobility. In this video I took in the Atacama Desert, you can see mini Rex attempting to climb a slope that is too steep for it and it falls over. So what we can do here is have K-Rex2, a larger rover with better mobility, carve a path for mini Rex so that it can cover the terrain. So we see here that K-Rex spun its wheel faster to dig through this step. And now mini Rex is able to make it out of this watershed and continue onwards. So you could imagine on a mixed mobility mission that's perhaps longer duration, having more capable but larger rovers carve paths for smaller robots to perform monitoring or other tasks where they might repeatedly be covering an area, and then let the big rover go off and do its important things farther away. Could also envision having the rover alter terrain for itself. We can also use non-prehensile terrain manipulation for other forms of mission aid, such as possibly landing site preparation. Maybe for Mars sample return, we'll have a landing vehicle coming down onto the Martian surface, and we could have a rover prepare the area nearby to where it's been caching samples to make a more level and smooth surface. Could also envision using rovers to help set up habitats for astronauts, perhaps digging trenches to lay cables in as part of habitat construction. So there's a lot of potential things we can do with non-prehensile terrain manipulation, and there's a lot more things to cover than I can do in one PhD. So we're going to focus in on one specific action and zero in on this. We're looking mostly at the trenching action here, where we use a wheel to dig, because it's very useful and it has pretty minimal requirements, so it's achievable. The purpose of trenching is either site mobility, site prep, science, and there's possible extensions to mobility as well, especially science looking at doing subsurface sampling. The robot operation, or what we need to do physically to control the robot to do this, is to drag, reverse, or spin one wheel at an odd speed while driving with the other three. Our rovers are all capable of doing that. And some potential mission scenarios this can apply to are accessing lower levels of strata for sampling, preparing sites for humans or other robots, such as by digging a trench to lay wires in, like I mentioned earlier. And our requirements are things that most rovers meet. So we need wheels with steer and drive motors. All of our upcoming and current rovers have that. For sensing, we'd like to have visual depth and orientation sensing to confirm that we've done things correctly. But if we have good enough open loop, we don't need to have these in real time. We'd just like to have them present on our rover. And for the terrain, we want friable soil and small rocks. So soft soil or small rocks. And this describes a large portion of both the lunar and Martian surfaces. However, to trench autonomously, we're going to need better models. Why do we care about this autonomy? Some amounts required due to communication delays. While the communication time to the lunar surface is pretty minimal, for Mars, we're looking at a minimum of 13-minute communication delays. If we want to do anything that is potentially risky to the rover, we definitely need to know it's going to work before we tell the rover to do it, because by the time we find out something's gone wrong, it'll be too late and we'll be stuck. We really don't want to get stuck. If we get our car stuck here on Earth, that's okay. You call a friend and they pull you out. If you get your rover stuck on Mars, there's no one to call and pull you out. And it's often end of mission. We don't want to do that. We'd also like to have relatively fast models, either so that we can do onboard simulation or so that we can use optimization methods to generate our actions for doing trench digging. However, fast models of wheel-soil interaction, both the forces and the soil motion that are applicable to both trenching and mobility degradation don't yet exist. So now I will talk about how I made them. First up, we're going to talk about the soil flow model. There's a couple options in the literature for modeling soil flow. Discrete element models, which use many small particles and model the individual movement of the particles, are pretty common for if you want visually realistic simulation. These are extremely slow, and you still need to know a lot about what your particles are like. Finite element methods are a little bit faster. They tend to be mesh-based methods. It's going to be faster, but still pretty slow. Hybrid DEM and FEM methods exist that sort of balance the two in terms of realisticness and speed. But all of these are way more computationally expensive than we'd like, and not something that's really suitable for use in an optimization or in really good online simulation. We also don't care that much about where every grain of sand goes. We want a general overall picture of what the soil looks like. So with that in mind, I developed a 2D closed form model of soil flow based on soil mechanics that describes a couple of distinct trench shapes that we observed by driving a wheel through soil. So we can see here, you can get trenches with a pointy bottom, trenches with a flat bottom, trenches that are somewhere in between where there's a little step in the middle and then either a pointy or a flat bottom. So we've got a couple of distinct trench shapes with pretty crisp edges that are easy to describe when we're looking at soft soil. This model is based on some key assumptions. We're assuming that all soil moves from the front to the back of the wheel without compaction. That's going to vary by terrain. And if there is some compaction, that will change our model accuracy a bit. And we're going to assume that the soil comes to rest at its angle of repose. The angle of repose being the maximum slope angle for a soft soil. So if you pile up sand and let it fall down, it's going to fall to the same angle every time. That's the angle of repose. It's a pretty easy to extract soil property. So let's go through how the soil flow model works just briefly. So here we're looking at a wheel from behind. First up, we look at where the wheel is interacting with the soil, and we separate the soil into the portions that are touching the wheel rim and the portions that are touching the wheel face. We separate those out. We'll also additionally, from the wheel rim, take out the soil that is getting caught up in the grousers rather than getting pushed along by the wheel rim, and we'll separate that out for now. We then take the soil that we've had flow around the sides, both around the face and around the wheel rim, and we'll pile it up to either side of the wheel. And then we let those piles reflow back into the trench. We've still got our soil that's separated in the grousers held out for now. Once we've reflowed those piles, we'll check and see if the resultant depth of our trench is physically possible. It may be that in order for us to have a pointy trench, we need to have a trench that's deeper than the bottom of our wheel. That's non-physical. If that's the case, we know that the bottom of our trench is flat, and we recalculate. And then once we've done that, we take the soil that was deposited in the grousers and we dump it back on the trench where it forms a step or a flat bottom. So I tested this in a lab environment using a single wheel moving through prepared soil, and scanned the trench at multiple points along its location to figure out what the shape of that profile is. You can see in this image here, we have in blue those LiDAR scans of the trenches, compared to in red the predicted shape of the trenches that we would expect to see. On the y-axis is effectively speed. That's the slip ratio, which I'll go into more detail later, but think about it as rotational speed for now. And you can see on the x-axis, we have the angle that our wheel is at relative to its direction of travel. So this is a pretty good fit, and we can predict the general shape of a trench for all kinds of angles of wheel and all kinds of speeds. We're covering a very large range here. Now it works in the lab. Does it work in the field? I also took this trench model and compared it to the shape of trenches that were dug in the Atacama Desert. So this is the K-Rex-2 rover again, which I got to tag along on a NASA trip to go run some tests in the Atacama Desert, which is a common Martian analog. It's used as a Martian analog environment because of its extremely low rainfall, which is nice because it means the soil is very dry here. And so we've got this very dry, soft soil. One interesting thing you can see in this video, it might be a little hard for people in the room because the screen's a little dim, but you can see some white streaks in the bottom of that trench dug by the wheel. Those show the presence of salt deposits or halites in the soil, which is not something you can see from the undisturbed surface on the top, but by digging just a little bit below the surface and getting past weathering, we're able to see the presence of salt deposits that we couldn't otherwise observe. So the model also worked well at predicting the shape of these trenches in the field. We were able to measure the soil angle of repose in situ by digging with the wheel and measuring the slope of the resultant soil pile. And based on that, we were able to predict pretty well what the shape of the trench would be. So this works both in the lab and in the real world, and it's extremely fast because it's closed form. But now we need to know about what our wheel-soil interaction forces are. So now we're going to talk about terramechanics. There's a couple of options for modeling wheel-soil interaction forces. First up, the one I'll talk most about today is Terramechanics, which is a semi-empirical model that uses soil mechanics informed methods to look at the stress distributions under a wheel. There's also, again, discrete element methods like we had for our soil flow modeling, where you look at many small particles, and finite element methods, which are generally mesh-based. These include methods such as soil contact model and resistive force theory, which is inspired by fluid dynamics. Terramechanics is generally the fastest of these, given that we're not simulating individual elements. So let's talk more about terramechanics. Terramechanics models give forces on the wheel for a specified driving state most of the time. How do we define that driving state? First up, we're going to look at the slip ratio, which I briefly mentioned earlier. The slip ratio is going to describe how our wheel is moving relative to the soil by looking at its rotational speed compared to its translational speed. So we'll be in positive slip if our wheel is spinning faster than it's moving forward, and in negative slip or skid if it's spinning slower than it's moving forward. Zero slip is the point where the wheel is moving, rotating with its rim speed at the same speed as its translational speed. So when you're driving your car on the freeway, you're at zero slip. When you slam on the brakes, you're in skid or negative slip. And if you're at the stoplight trying to race the person next to you and you slam on the accelerator and your tires spin before you start getting traction, you'll be in positive slip there. We're also going to talk about the slip angle, which is the angle of the wheel relative to the direction of travel. If our rover is driving straight, that's just going to be the angle of wheel relative to the frame. So for a given slip ratio S and slip angle beta and some known applied load, we can find the stresses on the wheel surfaces and integrate to find the net forces and how far that wheel is sinking into the soil at steady state. It is important to note that terramechanics models are generally steady state. However, there are some drawbacks to the standard models, which I'll be addressing. First up, we need to model small wheels that are at odd speeds and odd steering angles, which is all outside of the scope of normal terramechanics models. So because terramechanics is semi-empirical and we have many tuned variables, it really matters what region we've tested our models in and what region we've verified our models in when we're looking at the state space. Because these models are intended originally for the evaluation of tractive ability, they tend to assume that the wheel is driving straight and usually that it's driving and not braking. So we're in slip, not skid. There has been some exploration of skid, but not as much as slip. And there haven't been any that connect skid and non-zero steering angles. So I've built a new terramechanics model that fixes these problems. First up, one thing we do is we use the soil flow model to compute some of our wheel-soil interaction geometry without tuning. So we're able to use that soil flow model to eliminate some tuning variables, which makes us able to apply it to more conditions without as much tuning. I also combined models that handle slip angles and skid conditions and tested them. No one's ever done this before. There are no papers in the literature that look at skid with a steering angle. I also modeled the forces on the wheel's face using soil cutting theory. There are existing models that look at steering angle, but the most popular one has a math mistake, so we did it a slightly different way. And I also looked at how to predict tuning variables for different slip angles so that we can take this model and continuously apply it to any wheel state. So I'll talk briefly about how we can use the soil flow model to get our wheel soil contact geometry. So here we can see the wheel viewed from the front. And you can see we've got our soil surface here. And there's a couple of angles here that are going to define how our wheel is in contact with the soil. So we define our contact points by their angular location on the wheel's surface, getting into contact, where theta F is our front angle. It's largely determined by the sinkage. And theta R is our rear angle, which is where the back of the wheel loses contact with the terrain. And historically, that value has been either just straight up measured or tuned based on trying to fit the model better. However, we can do better. We've got a soil flow model. So here you can see the wheel viewed from behind now. And we've already executed our soil flow model to get this profile. And what we can do is look at the part of the profile that's in contact with the wheel's rear rim and take a weighted average to find out what angle the wheel is contacting the soil at. And we can directly extract that angle. And so now we don't have to tune this exit angle. We don't have to tune our wheel soil contact geometry, and we can just directly predict it and use that in our model. And because the soil flow model is closed form, this isn't going to add to our computation time. So we built this great model. How do we know it works? So due to the pandemic, I was unable to go borrow a Terramechanics test bed to test this, and I built one myself. So in this test bed, the wheel is driven at a selected travel speed, rotational speed, and angle. The wheel is free to translate vertically, and we measure the sinkage. So we've got a constant load applied to it in the form of a constant weight with free vertical translation. There's a force torque sensor mounted above the wheel, which will be a little easier to see on the next slide. And we're using the same soil as we used for both our soil flow model tests, and that we'll use in some tests later as well. And this also has automatic soil preparation with both raking and smoothing of the soil surface. So we have an even and consistently prepared soil bed. You can see on the left here is a wheel doing a run. Mounted above it is the force torque sensor here that's measuring our vertical load, so we know how much force is really being applied, and also measuring our forward and sideways forces. And you can see that it is digging into the soil pretty deeply here, driving at a relatively high slip angle. As you can see on the right, we had pretty good fit from the Terramechanics model for predicting both the X and Y forces on the wheel, as well as predicting the wheel's sinkage. I've shown here the same model, both with the soil flow prediction of the exit angle and without the soil flow prediction of the exit angle, using the classic method of just tuning that exit angle to make the forces fit as best as possible. So now we've got these models, what can we do with them? So with the soil flow and Terramechanics models, we now have the tools that we need to automatically design off-nominal driving strategies. There's two main objectives. One is to generate trenching actions automatically, and the other is to compensate for wheel failure. We can use the same approach to both problems. I will say that setting this up as an optimization problem is tricky. We're using a numerical model for a problem with pretty narrow feasibility region. I won't get into the dirty details, but suffice to say, it's more than just fmincon solve this problem for me. So here's how we would use an optimization-based method to generate trench actions. Our decision variables are going to be the rotational speed, the slip angle, the vertical load, and the sinkage for every wheel independently. So we've got 16 variables. And our constraints, first off, are going to be that our forces and moments on the entire rover sum to 0. So we want our rover to be driving at steady state because we want this to be an open loop action that we can perform and have the rover drive at a constant heading. So we need all the forces and moments to balance to zero. We also want to make sure that the vertical load matches the force predicted from the selected sinkage. Note that I've had the vertical load and the sinkage be both decision variables. This allows us to avoid having to do an internal loop in our Terramechanics model to perform finding of the sinkage. Normally we do that by having binary search over sinkage until our applied load matches our predicted vertical load. But if you do that in an optimization, you're going to have a bad time. So we avoid doing that entirely and set that as a constraint and let the optimization do the sinkage finding for us. Then we want to think about what we want our trench to look like. So for the trench that I wanted to dig, I wanted to have a clean edge, which is to say I wanted the soil piled all to one side and completely transported from one side to the other so that we have an area where no soil has reflowed into the trench. And I wanted some minimum dimensions. So I wanted the trench to be at least 2.5 centimeters deep so we could get a look at it. The cost function, since this is an optimization, is going to be trying to minimize our power consumption. There are, of course, an infinite number of possible ways to solve for force balance and solve these constraints, and a lot of them are going to be absolutely bonkers and have the wheels spinning crazy fast and working against each other. By minimizing the power consumption, we can counter that. So that'll generate us a feed-forward controller or an open-loop controller, or sorry, action. If we want to develop closed-loop control, we can do a very similar approach. So our decision variables, costs, and constraints are going to be the same, except that for controlling our yaw angle, we'll offset our yaw moment balance by a small amount. And for controlling our horizontal position, we'll offset the y force balance by a small amount. You could use the same approach to generate controllers that'll keep you at a constant speed by offsetting the x force, etc. But I focused on those two because I was mostly concerned with how do we drive straight. You then run the optimization separately for each controller, and you subtract out the feed forward driving variables in order to get a steering controller. You can then use PID on the rover heading and position with output to force your rover to drive straight. So after generating these trenching strategies, I tested them at CMU in one of David Weddergreen's test beds on a mini rover that I built. This rover has 4 wheels with independent drive and steering motors and a passive pivot for the 2 rockers. So it's got the same kinematics as K-Rex 2. It's got a RealSense T265 mounted to the front for measuring rover pose. And it's got the same soil preparation and same soil as the Terramechanics and soil flow model tests. We've got about a 1 meter by 2 meter area to work with, so there's room for it to drive. This rover is about the size of a microwave, so it's pretty small compared to K-Rex, which was about the size of a golf cart. This has the same wheels as our Terramechanics tests, which is great because we've tuned our models for them. So first off, for trenching, our open and closed loop strategies both worked well. You can see on the left, we have our open loop or feed forward only trench digging strategy. And on the right, we have that feed forward term, also with the feedback controls I described in a previous slide. And you can see that for all of these, the rover is driving straight. You can see the yaw error and y error on the right. They're staying pretty small. Our yaw error is at most like 1 or 2 degrees, and our y error is very small. And you can see on the lower right, the shape of the trench we dug, a laser scan of it compared to the shape we expected. Our sinkage was a little bit lower than predicted, but the overall shape was correct. All right, we can also use this same optimization strategy to compensate for actuator failure. We're going to have our same decision variables, our rotational speed, our slip angle, our vertical load, and our sinkage for each wheel. So 16 variables again. And the constraints are going to start off the same. We want the same force and moment balance to sum to 0. Once again, we're making the optimization do sinkage finding for us so we can avoid doing that internal loop. But now, instead of having trench constraints, we're going to have our broken actuator constraints. So I'm going to look at 2 different potential modes of failure here. There are so many ways a rover can break, but I only had time to test 2. So we've got, first up, we've got a stuck steering angle. So as if the rover's steering joint has gotten stuck in the middle of performing a turn or something. This did happen to Spirit. It got one of its steering motors stuck at an angle. And then we're going to look at a speed limited wheel. So here I'm going to set that the rear right wheel is only able to rotate at most half the speed of its intended travel speed. Now you could just slow down the whole rover, but let's say we're trying to cover 1,000 kilometers in less than 50 years, and we'd like to go fast. We want to know, can we go fast with this wheel? Maybe it just needs to recirculate lubricant for a bit and we have to run it slower for a bit. Or you need to know, do we absolutely have to go slower? And once again, we're going to minimize power consumption as our cost. You could imagine adding in other constraints as well, such as if you said, oh, we know that doing this kind of thing is going to put a lot of stress on one of the supports for our wheel. You can do things like set constraints limiting forces, internal forces on the rover, etc. I wasn't worried about that here, so I didn't include those, but you absolutely can. So compensation for stuck steering on the mini rover worked. On the left, you can see the rover driving with a stuck steer motor with no compensation. You can see it as the yellow track on the right over here, where it veers way off to the side. In the center, you can see our feed forward only turn. Where the rover has far less error in the Y direction, it does have some yaw error now though, so this one's not quite perfect. And with both feed forward and feedback control, we're able to drive completely straight. That's the blue track. Compensation for a wheel with a speed limit on the rear right wheel worked really well as well. You can see here, again, on the left, we have our fully uncompensated rover, and you'll see that it immediately starts turning off to the right, and it's going to end up in the ditch off to the side. Our feed forward only turn, which is the red track, is able to drive completely straight. And our feed forward and feedback control, again, is also able to drive completely straight, which is not surprising given that the feed forward only turn worked. You don't really need feedback control there, but it still works too. So this tells us about how we can do a single driving strategy. It doesn't tell us as much about our overall mobility. If we want to look at how our overall capabilities have been affected by the loss of a drive motor or steering actuator, how do we do that? So what we've done so far is to do this through testing. So what you can do if you want to look at, say, what regions of slopes can we traverse, is you can do tests where you have your rover attached to a tether and apply a fixed load to that tether and see how the rover is able to drive. So this is drawbar pull testing. So we did some of this with Viper at NASA Glenn. Shout out to Arno, Antoine, and the Viper team for recording this data for me. And so what we do here in this video, you can see the front right motor is stuck, steering motor is stuck at about a 30-degree angle, and the rover's driving forwards. And so we can do that and also do free driving tests where we just let the rover drive untethered. Those cables there are just power and communications, not an actual tether. And then we can look at how much slip gets induced on the rover while it's doing these maneuvers. We can take the applied load to our rover and convert that into an equivalent slope that it would be driving up if it had to pull that much weight, and use that to figure out how much slip gets induced on the rover due to failure of an actuator. However, this is only showing the worst case. If we're doing our failure compensation strategies, we're going to have better mobility than we can see here.
Kathy, can you explain what's happening in the video on the right there? What is the failure mode? I see
Oh,
the
yeah.
wheels in the air, but what is failing?
That one is a stuck suspension motor where one of the wheels has been raised up. So this is a failure mode that you can see on Viper, but you would not see probably on Curiosity, Perseverance, any of the ones with passive suspension. This is one of the downsides of having an active suspension is you risk this happening.
I think that does happen on very opportunity,
Oh yeah.
right? If one of the three wheels on one side of the road.
Mm-hmm. Over like rough terrain. Yeah. Yeah. So we can also use driving strategy generation to assess this kind of impact of actuator failure. So while a single driving strategy only tells us that driving is possible, it doesn't tell us the scope of what's possible. We can simulate doing these drawbar pull tests by changing the force balance on our rover and rerunning the optimization. If we then use those results, we can get operational limits on how we're able to drive our rover with our new affected mobility. This plot on the left that you can see here is for the mini rover, where we have plots of the slip induced for the rover with different failure modes. Green is just our normal nominal driving, looking at how much slip we get on a wheel for different angles of slope. In red, you can see if we have one of the steering motors stuck at a 50-degree angle, how much slip is induced on the rover. And in the blue, you can see if we have that speed limited wheel. So notably, if we have a speed limited wheel, the maximum slope it can even go up is going to be 2.5 degrees. And when we have a stuck steer actuator, the maximum slope is going to be 10 degrees. But those are going to be at very high amounts of slip, where we're looking at a higher risk of embedding. For example, Viper has an operational limit of 40% slip, or 0.4, in order to avoid being embedded. If we were to set an operational limit of 40% slip here, we would be restricted to flat ground with a stuck steer motor, and we wouldn't be able to drive at all safely with our speed limited wheel. If we had that as our operational constraint and wanted to keep that and not modify it, we would know that with a speed limited wheel, while it is technically possible to drive, we wouldn't think it's safe and we'd want to slow down the whole rover. So conclusion, let's talk about what we've learned so far. So we can use non-prehensile terrain manipulation to dig trenches while we're driving. We can now model soil flow efficiently and quickly in a way that is suitable for use in other modeling methods and in optimizations. We can also now accurately model terramechanics for off-nominal driving of various forms. And with these models, we can make driving strategies for digging trenches and for dealing with the case of mobility system failure. Our open loop driving strategies also work well, which is great because it means we can use these techniques on rovers as they are now and rovers as they're likely to be in the near future, at least for large flagship missions. So here's what we've done so far, but what's next? This is a really cool area and there's a lot more to do. Non-prehensile terrain manipulation. We'd like to do more exploration of the different actions we can do and develop them more for rovers. We could also do more with just the trenching action. It has potential applications to steep slope mobility through carving paths or controlling the sinkage of wheels, such as by intentionally sinking wheels to provide anchoring while driving down steep soft slopes, or perhaps controlling the roll of the rover while traversing slopes. We can also go back the other direction and try to design our rovers and wheels for non-prehensile terrain manipulation. So we could imagine running the same optimization, but perhaps where our wheel radius or our browser dimensions are a free variable, and we can optimize those. We also would like to do kinodynamic planning for larger scale terrain manipulations. So we can do stuff like search for shallow subsurface ice on the lunar surface through explicit paths, or even do terraforming on the Martian surface. What's next for mobility degradation? So we'd like to expand to more soils and wheels. I've been looking primarily at a mini rover, and we want to look at tuning our models for larger rovers before deploying them in space. Also like to look at more rover architectures. So as I've mentioned, a number of different rovers have different kinematics, and we could also imagine expanding this to legged robots and other different forms of locomotion as well. I'd also like to expand to more failure modes. I've tested 2 so far. There are a lot more ways that rovers can fail. So I have a lot of people to thank for this work. First up, funding. This work was funded by a NASA Space Technology Research Fellowship, a NASA SBIR STTR grant, a CMU Presidential Fellowship, and the CMU Department of Mechanical Engineering. Couldn't have done it without their help. But most importantly, I'd like to thank Aaron. It has been a pleasure and an honor to work with you for the last 6.5 years, and I have loved getting to help be a part of the creation of the Rover Mechanics Lab. Yeah, and I'd love to thank my committee. David, thank you so much for letting me borrow your test bed and your sand all the time. Literally couldn't have done any of these experiments without you. Dimmy, it's been wonderful having your insight and guidance through this process and talking about Terramechanics. And Terry, who's not here, for your incredible passion, especially about non-prehensile terrain manipulation. It has been so much fun and a pleasure to work with all of you. I'd like to thank the lab, Rover Mechanics Lab. You are the best lab I know. You're a great group of people. Okay. Especially I'd like to shout out to Jesse and Brian for helping with doing some of the code for making the mini rover work, and Kiara for helping run all of my experiments in December and November. I'd also like to thank IRG group at NASA, especially Arno, my NASA collaborator, for the duration of my fellowship, and everyone on the ARADS team. I couldn't have done any of my rover experiments in the Atacama or at Ames without all of your help. And also shout out to all of the other IRG and STRF fellows. It's been a lot of fun working with you. I also couldn't have done this without the support of my friends and family, especially my parents who flew out here today, and my partner James who flew out to be here this week. And also the Explorers Club of Pittsburgh for helping keep me grounded by taking me to new heights. So, thank you.